Welcome to the continuation of our polar section of our complex number series in our maths module. I'm going to start by saying that this involves some work with series, so you should take a look, if you struggle with series, at my playlist on series and also in the maths module. And I should also say most people struggle to get their head around this a little bit, so if you find that's true for you, rewatch the video again and hopefully you should definitely get it the second time round. So we're just going to carry on where we left off. Finally, on the final part of my last video, I said that z could also be represented by r by e raised to I by theta. And I said I'd show you why this is true, and that's what I'm going to do. So I've wrote down some series here, and these are the Maclaurin series by Colin Maclaurin. And it was actually Euler who discovered that this is actually true. So if we have a look at these series, you'll notice what they start on. So this starts on x to the 0, this starts on x to the 1. They go up on the cos in every even power, on the sine in every odd power, and they alternate the signs minus, plus, minus, plus going across. Whereas e raised to the x goes from x to the 0, x to the 1, 2, 3, 4, all the way up, and the signs never swap. And also notice they're all over the factorials, where this is over 1 factorial, this is over 1 factorial, this is over 1 factorial, and this is over 0 factorial, where 0 factorial is also equal to 1, and I do have another video on that. So what we're going to do is we're going to sub in our parts which we had. So we know that our number can be given by z equals r cos theta plus I r sine theta. But we factored out r. So z equals r cos theta plus I sine theta. And we're looking to make z equals r e to the I theta. So what we know to be true from this is that e to the I theta must be equal then to cos theta plus I sine theta. So to do this, we're going to use the series. So we're going to start with the cosine, and all we have here, remembering that these are a function, so this can be treated as a function of x, function of x, and function of x. So for the cosine, this is now just going to be a function of theta, and it's just going to be given by subbing in all the values of theta. For sine, however, this is going to be I multiplied by a function of theta, and for e, this is a function of I and theta. Now, to really get across my point here, what I'm saying is this is a function of theta, this is I by a function of theta, and this is a function of I theta. I'm really stressing the point here because when we come to put these values into the series, this is where most people's confusion comes in. And we're going to show you why now. We'll start off with cos, and for cosine, we'll just put in all of our values of theta. So we have 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial minus theta to the 6 over 6 factorial. And we're only going to do it to that many terms. We'll then take sine. And now this is I sine theta. So what we're going to do is we're going to multiply each one of sine's terms by I. So we have I theta. We'll just lower this down a bit, sorry, because we've not got much room. So we'll do I theta minus I theta cubed over 3 factorial plus I theta to the 5 over 5 factorial minus I theta to the 7 over 7 factorial. Noticing that i's are in front of each of the individual terms. And then finally, I'm going to take e to the I theta. And this time, the e is going to be subbed in where each of the x's are. So what we have is we have 1 plus I theta plus I squared theta squared over 2 factorial plus I cubed theta cubed over 3 factorial plus I to the 4 theta to the 4 to the 4 factorial, and we'll do the final term of I to the 5 theta to the 5 all over 5 factorial. So then we can rewrite e down now, and we can say then e equals, remembering our series going through I being I minus 1 minus I, 1. So we go 1 plus I theta, so we have I squared, so that's minus 1, so minus theta squared over 2 factorial, plus we have I to the 3, so that's minus I, so we can get rid of our plus sign and say minus I theta cubed over 3 factorial. Our 4 goes back to 1, so there's no term there. So that's theta to the 4 over 4 factorial. And then we get back to 5 again, we go back to our first position and we get I. So plus I theta to the 5 factorial. Now that might seem a little bit confusing at the moment. And what we're now going to do from there is we're going to take a sum of our cosine and our I sine series, and we're going to compare it to our e to the I theta series. So we'll do each of the terms and we'll do them in order of the magnitude of theta. So cosine comes first, with it being theta to the 0. So we have 1, and then sine, which is plus I theta, and then it's cosine, and then sine, cosine, sine. It alternates like that. So we get I theta minus theta squared over 2 factorial minus I theta cubed over 3 factorial plus theta to the 4 over 4 factorial plus I theta 5 over 5 factorial minus theta 6 over 6 factorial minus I theta 7 over 7 factorial. And this is the series here for cos theta plus I sine theta. And now if we compare the two series, we'll see 1 I theta minus theta squared over 2 factorial minus I, and we just go across, look at all of the terms, and you'll see they are actually the same. So we can say now that cos theta plus I sine theta is equal to e to the I theta, and therefore z can be given as z equals r e to the I theta.